Hi, this is Brian Fogarty, and this is a video for Chapter 14 of the book Quantitative Social Science Data with R, 2nd edition. So this is our first video of the chapter. This chapter is on count models, count regression models. And so specifically in this video, we are going to take a look at the data that we're going to use, or that's used in the chapter, and also the Poisson Regression model. So I've opened up and saved a new R Markdown file. I'm going to set the library path and the working directory. Okay, so the Poisson Regression model. So I include a discussion, a fairly brief discussion, because I could kind of go on and on in the chapter about Poisson regression, and then as well as negative binomial regression. Underlying all of this is something known as the Poisson distribution, which is applied for count data. So what are count data, right? So what we're looking at are discrete counts. So right, you want to think of it this way, integers, right? So something it can be like 0, 1, 2, etc., but it can't be like 0.5. And we're looking at it as cross-section. So we're not looking at counts over time. That, for that we would be using say time series count models. So these are the discrete time. Sorry, that's not the right word. Discrete counts for cross-sections. Now, the data you have could be from, collected from over a time point. It's just that the unit, you don't have like a time unit involved. All right, so the Poisson regression model is the simplest one. It comes directly out of the Poisson distribution. There is a critical assumption that's part of this, and that is that the mean equals the variance of our count variable. When this is the case, it's known as equidispersion. The problem, which we'll see, is that it's very rarely the case, at least based on the data I've worked with, and I've done a lot with count models. It's very rarely the case that we have equidispersion. Usually we have the variance being larger than the mean. This is known as overdispersion. Again, so normally that is the case. We have overdispersion. It's just a question of how much overdispersion, or how bad is the overdispersion. The reason why we care so much about this is that if overdispersion is present and we use a Poisson regression model, the predictor standard errors will be biased downwards, so they will be smaller than what they should be. Since they're smaller than what they should be, since they're biased downwards, that means that we're more likely to find predictors being statistically, or showing up as statistically significant, and they might not actually be. It could just be effect of overdispersion that we're not taking into account. So that's really the big problem with Poisson regression models. And again, it's not that you should never use Poisson regression models. It's just that since overdispersion is so ubiquitous that it's rarely the best thing to use. The solution, the simple solution, is to use negative binomial regression models, which we'll look at in the next video. And that takes into account overdispersion, actually models it. And one of the nice features of negative binomial is that if overdispersion is not present, it actually collapses to a Poisson regression. So it's equivalent. All right, we're getting a little ahead of ourselves. So in the chapter, I talk about Poisson regression, negative binomial, and we also talk about something known as zero inflation, or a problem with XX zeros, which some of the videos that we'll do in this chapter cover. There are tons and tons and tons of different types of count models. Part of the reason is that when we're working with count data, a lot of our effort is trying to essentially diagnose the data, figure out like what is the correct, quote unquote, correct model or best model to use. Trying to find things that give us the sort of best representation of the data generating process. All right, so this is part of us going into this. All right, let's get into the data and applying all this in R. All right, so we are going to use data from an article by Clark et al. I might be mispronouncing the name. Apologies. From an article in 2020, and they have count data based on the number of citations over a handful of years of papers or articles that appeared in a set of high-impact social science journals. I think it was mostly political science and communication journals. And what they were interested in seeing is, well, there's a few things, but one was, do people who promote their publications on Twitter, do they have more citations of those articles than people who do not? They were also interested in sort of if there's any kind of sort of a systematic effects within that. So for instance, does it matter if it's a woman or a man promoting it? Like what's those kind of effects? So we are going to use data that's kind of a subset of, or one part of the data that they have originally in that article to look at count data modeling. All right, so let's read in the data and get started. All right, so we're going to load tidyverse. All right, we're going to read in the data. I'm going to save it as citations. So that's going to be a data object. It's a CSV file, that's what we have it saved as. So read underscore CSV, and it's called citations Twitter. Okay. So let's read that. So it read in well. We see there's 308 observations, 7 variables. Let's take a quick look at it using Glimpse. Okay, so we have a handful of variables here. Let's see. We have article sites. That's our outcome variable. Woman lead author. So the dummy variable is the lead author a woman. Woman author. So is at least one of the authors a woman. Tweetdom, which is did anyone tweet about the article? Full prof is whether at least one of the authors was a full professor. That means like a full rank professor. So the idea is they may be more prestigious, so people know their names, so they might be more likely to cite the article, given that. And then we have retweets and total fav, tot fav. All right, so retweets are pretty straightforward. So how many retweets did the article get? And then total, tot, I should say it like it is, tot fav. Total favorites, so how many times it was favorited. So one of the things about this data, or these two variables, right, is that in order for there to be a value here, the person needed to have tweeted about it. So that's what all these NAs are. So if we were including this in a regression, then it's going to reduce our number of observations. Okay, so let's do, I'm going to go through this kind of quickly, but one of the good things to do when we're starting to work with count data is to take a look at the descriptives on our outcome variable. So let's do summary, citations, and then article cites. Okay, so we see the mean is 3.05. So just a few comments. The number of citations that articles get is very contingent on the field. That's where, if you've seen impact factors of journals, there's a large variance between the sort of what are considered good impact factors in one field versus another. There's a number of reasons for that, but if you're looking at this saying like it's only 3, like that might be pretty good for a field, or it might be terrible for a different field. It's also the case that this is somewhat restricted data, because I think they looked at it like 3 years or something like that after it was originally published. So obviously, as the more time goes on, in the sort of publication workflow, there might be a lot more sites of this. So it's not like this is the end of the story, if you will. But this is what the data we're working with. All right, so let's also look at the variance using var function, citation, article cites. Right, okay. So you see here that we included this and we get an NA. All right, so we know like that's not right. The reason we got that is because this data has an NA in it. So if we use the mean function, we get the same thing. So what we need to do in the var specification is include an option na.remove equals true. All right, so we see that the variance is 13.33. So the mean is 3.05, variance is 13.33. So yeah, the variance is larger than the mean, a lot larger. So we do not have equidispersion. The question that we'll answer as part of this as we go forward is the overdispersion that exists, is it large enough to cause a problem? Spoiler alert, it is. All right. Another thing I like to do, and I'll try to do this quickly here, is to look at, to plot the outcome variable. So let's do that here. I'm going to do it real quick. We're going to use our standard ggplot stuff. We're going to filter out that missing value, okay, that we've done before. So filter not is NA, article cites. All right, we're using our piping here. Come back, ggplot. We're not going to make this all nice and fancy, just because we want it as a diagnostic, really. Okay, ggplot. I'm going to do a smooth density plot here. So I'm going to use geom density mapping equals AES, and then article cites. I'm going to fill it with steel blue, and then we don't need to lighten it, but I do in the chapter just because it looks a little better. Alpha equals 0.5. Okay, and then I'm not going to even include, so we could include a label about the number of citations. Yeah, let's do it, let's be honest. Let's do labs equals x equals, sorry, labs open parenthesis x equals number citations plus, and then we'll use theme minimal. Okay, so that should work. We did it kind of quick. Hopefully there's no mistakes in here. Okay, so we get this plot. Click on zoom. I'm going to pull it. All right, so this is a very, very kind of standard distribution for a count variable. We have a peak of values, kind of a main mass of values on lower values, and then it kind of goes out with the higher values. So looking at this, there's, depending on how the distribution looks, that could give us a clue on if we need to use sort of exotic or non-standard count models. So for instance, there's a type of count model called the Poisson inverse Gaussian regression model that's used when we have this peak like this, but then observations that are like all the way out here, like really big tail of observations. There's other things like that where we might be looking and seeing like, okay, is there like a ridiculous number of zeros? Maybe we have a problem with zeros. But it's good to do just to get a sense of what the data looks like for our count variable. Okay. So let us run our Poisson regression model. All right. So this is taking the same, how we specify this is the same roughly as we've done before with all the other regression models. We're going to do summary wrapped around it, and we're going to save it as model.prm, okay, for Poisson regression model. And then we're going to use GLM, the GLM function we've seen before. We include our outcome variable article sites, tilde, and then for this example, we're going to use tweetdom, all right, woman, lead, author, and then full prof. Okay, so those are our three predictors. We're going to use these three predictors to predict article sites. Okay, then we'll do family equals Poisson, and then what our data is. So data equals, quote, citations. All right, so that's all in there. Let's highlight that and run that. And it does not like it because I put it in, why did I put it in quotes? Why I put it in quotes? That's a problem. All right. Okay, there we go. All right, let's see here. So the output looks similar to what we've seen before, right? We have AIC that we've talked about, which on its own is not useful, but it's useful for comparing models, which we're going to do in this chapter. Here are individual predictors. The same idea, we have our estimate, which is the regression coefficient, our standard error, z-value, which is just the estimate divided by the standard error, the exact p-value, and then stars, right? So again, there's redundant information here about figuring out what's statistically significant and what's not. So we see that tweetdom and full prof are statistically significant. So these significantly predict the number of article citations. They're both positive, so that means that if an article is tweeted about, is expected to have more citations, and if at least one of the authors is a full professor, then they're expected to the article is expected to have more citations. Just like with the other GLMs we looked at, we cannot directly interpret these coefficients, so we need to do a different way of doing it, like we've done before for GLMs. Okay. We're going to do next just a quick, we're going to do a test for overdispersion. This is, so there's a number of things we can do here. This is just a test on the Poisson regression model itself. We're going to do some stuff with the negative binomial as well later. Okay, so we're going to use a function from the package AER. So we need to load that. Well, there's a lot of stuff here that tells us what's going on. It's a lot of warnings here, or at least information. I guess it's, yeah, there is some warnings about what it's overriding. And the function is called dispersiontest model.prm. All right, then we put it in. Okay, so let's look at the results here. All right, the alternative hypothesis is that true dispersion is greater than 1. All right, what this means is that if it's equal to 1, then that is equidispersion. If it's greater than 1, that means that it's overdispersion. So the null here is that true dispersion would, so if the null was specified, it would be true dispersion is equal to 1. All right, again, equidispersion. Equidispersion. So what we're looking at is the p-value, okay? Looking to see whether or not it's equal to or less than 0.05. We see that it is, so we reject the null of equidispersion and accept the alternative. So what this means is that we have significant overdispersion, and so we should not be using the Poisson regression model. All right, that's it for this video. The next video we're going to look at negative binomial, where we pick this back up again and see what's different using negative binomial compared to the Poisson regression model. All right, so thanks for watching. I'll see you next time.